Bismillahirrahmanirrahim. Assalamu alaikum, students. Today we're going to discuss an important topic, an interesting topic. The topic is, let me state the topic, simple harmonic motion and uniform circular motion. This is our today's topic. Listen carefully and enjoy the lecture. And I underline it first. Simple harmonic motion, now you know it's a model oscillator, and how we define it, we have already discussed its definition, its energy considerations, and its equations of motion, its position time function, its velocity time function. We have discussed its acceleration time function. Then we discussed that its total energy remains constant throughout the motion, but kinetic and potential energies are oscillating. All those things we have discussed. And you know, uniform circular motion also. Uniform circular motion is simply what? It is circular motion at constant speed. Circular motion at constant speed. That means if there is a body which goes along a circle, its mass be m. So if it goes along a circle having center O, circle has some radius r, and if it covers equal distances in equal intervals of time, then we say its motion is uniform circular motion. So it is simply circular motion at constant speed. And you know, since it's the velocity of the particle is tangent to the path, here velocity vector is this way. At some other point, when mass reaches here, velocity vector will be this way, and some other point, when mass reaches here, this velocity vector will be this way. So since the velocity vector is changing direction with time as motion proceeds, acceleration is produced in the body. So its speed is constant. Speed means the magnitude of velocity vector is constant, but due to the change in the direction of the velocity vector with time, acceleration is produced. So it is an accelerated motion. You know all these things, I'm just refreshing your memory. So it's an accelerated motion because of the change in direction of the velocity vector. Acceleration is produced in the body. And the magnitude of acceleration vector, if a is the acceleration of the body, the magnitude of acceleration vector is v squared by r, where v is speed and r is the radius of the circle. This acceleration vector has direction towards the center. So if I show it this way, acceleration vector is pointing towards the center. At all positions, it will be pointing towards the center. Here it will be this way. Here at this instant, this vector will be pointing this way. So this acceleration vector is pointing toward the center at all positions. So we call it centripetal acceleration. Centripetal acceleration. Magnitude of the acceleration vector is constant because r is fixed and v is constant. So in uniform circular motion, if we summarize, velocity vector has constant magnitude, acceleration vector has constant magnitude, Both vectors are changing direction continuously and they are at right angles with each other. Velocity vector and acceleration vector are at right angles with each other, right? So this thing you keep in mind. Now, you know on one side, you know simple harmonic motion. What is it all about? Now you know the uniform circular motion also. Now, there is a relation between these two motions. I state that fact, then we will justify that. The relation is expressed through this statement. Let me use another color. I think I will use this one. The relation is simple harmonic motion can be described as the projection of a uniform circular motion along a diameter of the circle. Simple harmonic motion can be described as the projection of uniform circular motion along a diameter of the circle. This statement is the relation between simple harmonic motion and uniform circular motion. So let me justify it. So if there is a particle going in circle at constant speed, for example, this mass is going this way. Now, if you take diameter of this circle like this is center. Now, you draw perpendicular from the particle on the diameter. So here, let me denote this mass by P. P dash is the projection of this particle P having mass M on diameter. At some later instant when P reaches here, you draw the perpendicular on the diameter. The foot of perpendicular is called projection. So as this particle P moves in circle, its projection on the diameter P dash or P prime also moves. You can check. P reaches here, P prime reaches here. As we do the mathematics, when P goes along the circle at constant speed, this P prime, that it means its projection on the diameter of this circle also moves, and motion of P prime is complete this simple harmonic motion. Their time periods are equal. That is the meaning of this statement. That simple harmonic motion can be mathematically described as the projection of uniform circular motion along the diameter of the circle. So if a particle is going at constant speed in a circle, its projection on the diameter executes simple harmonic motion. So simple harmonic motion, therefore, can be mathematically handled using the uniform circular motion. So let us now establish that the motion of P prime is exactly simple harmonic motion. So let us move. I will draw a figure now. Let me draw the figure first, then we will proceed further. You can draw the figure with me. Let me use another color. This is x-axis, this is y-axis. Then I have another figure. This is x-axis, this is y-axis. Now another figure. Part A of the figure, sorry, part B, part C, and part D. This is figure 1. So in figure 1A, let me complete it. So in figure 1A, we have a particle P in uniform circular motion. Let its angular velocity be omega. So let omega be angular velocity of the particle, angular velocity of P, particle P. So this particle P is moving in circular motion, and let capital R be the radius of the circle. So let R be the radius of the circle. So R is the radius of the circle. Now this part A is the situation at t is equal to 0. This is situation at t is equal to 0 when motion starts. You can see this radius OP makes some angle, so we name it with the x-axis, this angle. Let this angle be phi. So at t is equal to 0, this particle P is moving, is shown in figure 1A, moving in the circle of radius r at angular velocity omega, and r is the radius, so length of OP is capital R, and this OP radius is making angle phi with the positive x-axis as shown, right? Now in figure 1B, we show the situation at time t. At time t, situation will be different. Let me draw the figure. This is P. This is OP. This is the projection on x-axis P prime. And there is a projection on y. We name that Q. Let me use another color here. This OP prime gives actually the position of P prime. We call this OP as x of t. This x of t and this angle here, this angle will be omega t plus phi. Why so? Because at t is equal to 0, this OP vector is making angle phi. So after time t, that is t time later, this angle will be increased to omega t plus phi, because omega is the angular velocity. That means in t time, OP vector will move through omega t angle. So already it had angle phi with x-axis. Now it will have omega t plus phi, right? So it's clear. I hope it's clear. Now you can see the projection of OP along the x-axis, or equivalently the x component of the radius vector corresponding to OP is, this distance x of t is r cos omega t plus phi. Let me name it first. This x of t is simply r, because OP is r. Let me write here r. This length is r. So this OP prime x of t distance is r cos omega t plus phi, right? Now you can see this is identical. This is identical with x of t is equal to xm cos omega t plus phi. The equation which we use it to describe the position of a simple harmonic oscillator. So this is identical. Only one thing is different. What is different? Instead of xm, we have r in this equation, right? That means this projection of P on x-axis, which is P prime, executes simple harmonic motion along the x-axis. Let me write, implies that P prime executes simple harmonic motion SHM along the x-axis, right? Now let us move to the velocity of this P prime, that is projection of P on x-axis. Let me draw another figure. So at time t, this particle P is here. Its projection P prime is here. This at time t. And this OP is making angle. This angle is omega t plus phi, as indicated in part B of the figure. This is omega t plus phi. And we know in uniform circular motion, as already discussed, the velocity is tangent to the circle at that point. So let us show that we are assuming this particle is moving in anti-clockwise sense this way. So let me use another color for that. So if v is the velocity of P, this v is the velocity vector of P, it will be this way tangent. And its projection on x-axis, that is this length, this projection of v on x-axis will give me velocity of P prime. So I call it Vx of P. Vx of T is simply the x component of the velocity vector v. Velocity vector v is representing the velocity of particle P moving in uniform circular motion, and its projection on the x-axis is Vx of t, right? So this Vx of t, when you find from this figure, from figure 1, this C, from figure 1C, Vx of t is minus omega r sine omega t plus phi. I name it second. Because where V is omega r. You know, if V is the linear velocity of the particle P moving in circle, omega is its angular velocity, then there is a relationship between linear velocity V and angular velocity omega. This V is r omega because this OP is r, radius of the circle. So when you find its projection Vx of t, which gives you velocity of the projection P prime along x-axis, this you will come to know that it is minus omega r sine omega t plus phi. Omega r is evident because it is just V sine omega t. Negative is because this projection Vx of t is pointing along negative x direction. So this is exercise for you. Check it. Check it at home. That Vx of t is minus omega r sine omega t plus phi from figure 1c, right? There is another way to get equation second, which gives you velocity of the projection P prime along the x-axis. You can do it by differentiating equation 1 with time because the derivative of position is velocity. So let us move to the acceleration now. Let me draw this figure again at time t. This is at time t. This is my OP. Its length is r. This angle is omega t plus phi, right? As we already discussed in uniform circular motion, at every point, at every position on the circle, the acceleration vector is pointing towards the center and its magnitude is constant. So at point P, this acceleration vector is like this. It's pointing towards the center. Now it will have some projection on the x-axis. That is, this is its projection. That projection I name ax of t. And as I said, that this ax of t will give me the acceleration of p prime, right? So from right from figure, again from figure 1D, that is this one, 1D. When you solve, let me write it neatly. From figure 1D, this ax of t is equal to minus omega r cos omega t plus phi. I name it equation 3. Why so? Because you know this A, that is acceleration of the particle moving in circle, is omega square r. You can check it. A is v square by r. V is r omega. when you make the substitution, you write r square omega square by r. We replace it v by r omega, and here I am using little r, and in this diagram I am using big R for the radius. So r will go, it will become r omega square. So r omega square is the acceleration of the particle p moving in the circle. In other words, r omega square is the length of this vector A. This r omega square is length of this vector A. So when you find its projection geometrically on the x-axis ax of t, from the figure you can see, you can check it, it will be minus omega square r cos omega t plus phi. Right? So you need to check it at home as well. Check this at home. As I said, in case of velocity, we can get equation 3 from equation 2 by differentiating velocity vx of t with time. So this equation 1 is now giving me the position of p dash. This second equation vx of t is giving me velocity of this p dash. This third equation ax of t gives me velocity of, acceleration of p dash. So you can see they are similar to the equations of simple harmonic motion. I have shown that only one thing is different, that xm is replaced by r. That means r, radius of the circle, becomes the amplitude of motion for the particle, for the p dash, which is executing simple harmonic motion. Right? So they match the equations of the simple harmonic motion. So it is mathematically established that if particle p goes along a circle at constant speed, then its projection on the diameter p prime is executing simple harmonic motion. Now let us move to this another projection which is on y-axis. Since circle lies in xy plane, so there is another projection of p on y-axis. This q, that's projection of p on y-axis, is also executing simple harmonic motion. You can see if I call this distance y of t, this distance y of t, which is projection of OP on y-axis, it will give me position of q, right? You can see from this figure, this y of t from figure, I think it is 1b. Yes, from figure 1b, y of t is r sine omega t plus phi. So it's also simple harmonic motion. So the projection on x is executing simple harmonic motion. The projection on y is also executing simple harmonic motion. Now you can see what is the difference. In this equation, we have cos omega t plus phi. In this equation, we have sine omega t plus phi. That means there's a phase difference between the simple harmonic motion going along x-axis and simple harmonic motion going along y-axis. So if you write it in terms of cos, you can write it r cos omega t plus phi minus pi by 2. R cos omega t plus phi minus pi by 2. That means there is 90-degree phase difference between the simple harmonic motion executed by P prime and simple harmonic motion executed by Q. Right? There is no difference in amplitude. Amplitude is R. There is no difference in angular frequency or time period. That is same. Here is omega. In the equation of x, there is also omega. So there is same time period, same amplitude, but difference in phase between the two simple harmonic motions. Let me name this equation 4. You can find Vy of t. We can find a y of t. How? Either you find it geometrically, you find y component of this velocity vector, that's its y projection, that will give you Vy of t, that is, will give you the velocity of q, and you can find a y of t geometrically by finding the y component of acceleration vector, right? Or you can differentiate this y of t with time, you will get Vy of t. You can find derivative of Vy of t with time to get Ay of t. So do that. Do this, find this at home. This is another home assignment. Find this, find this. Now, at all times, you can see one thing. At all times, what is true? X square plus y square is r square. That means if you square this x, which gives position of p prime, then you square this, which gives you position of q, you will get r square. You can see by inspection simply, if you do that from the figure, you can use Pythagoras Theorem. OP square is O, let me write it, hypotenuse square, that is OP square is OP prime square plus OQ square. This is OP prime square. This is here OQ square. OP prime is x of t, OQ is y of t. When you do the maths, cos square theta is here. Here you will have sine square theta, cos square theta plus sine square theta will be 1. You will get just x square plus y square is r square. Similarly, when you do Vx square plus Vy square, you will get V square. When you find Vy of t, you square that, you square Vx of t, then add those, you will get V square. Simple, because Vx and Vy are basically the rectangular components of V. V is the magnitude of the velocity vector of the particle going in circle. Vx and Vy are the velocities of P prime and Q, right? Another thing, when you do Ax and Ay, same is true here, Ax square plus Ay square, sorry, it is not plus here, it's equal to. So Vx square plus Vy square is V square, right? You can write it also omega r square, because V is omega r, as already discussed. X square plus Ay square is A square. Again, Ax and Ay are components of A. A is the acceleration of particle P, and Ax and Ay are accelerations of P prime and Q. And if you replace A by omega square r, you can write it omega square r whole square. So x square plus ay square always will be a square, which is omega square r whole square. Vx square plus vy square will be always v square, which is omega r whole square, and x square plus y square will be equal to r square. This is all your exercise. Check all this at home. check it at home. So let us move to now the conclusion. So we justified that simple harmonic motion can be described as the projection of uniform circular motion along a diameter of the circle. Note that the projection of uniform circular motion, as we said, along y direction also gives simple harmonic motion, x direction gives simple harmonic motion. It is true for projection along any direction. This fact is true for, let me write it neatly, true for projection along any direction, right? So in general terms, once you set up a circle, circular motion, uniform circular motion, some particle P going in a circular fashion at constant speed, if you take any line in the plane of the circle and see its projection on that line, that will execute simple harmonic motion, right? That has a proof. You can check that, Google that. That's not the issue. The conclusion is now, one is this, that simple harmonic motion can be described as a projection of uniform circular motion along a diameter of the circle. Second thing is, as we saw and justified, that two simple harmonic motions correspond to a uniform circular motion. So therefore, we can write the circular motion can be regarded as the combination of two simple harmonic motions at right angles with identical amplitudes and frequencies, but differing in phase by 90 degrees. These two conclusions you need to remember. As we saw, here you have cos omega t plus phi, and in y of t we have cos omega t plus phi minus pi by 2. So this all for today. Go through all the lectures, make a notebook to all the assignments which I give through the lecture or otherwise, and do not forget to like, share and subscribe my channel. You can also give comment in the comment box. Thank you. God bless you. Assalamu alaikum.